Any other questions? You guys okay? All right. We're covering lighting and noise today, and another topic that I find kind of fun, and it's about our senses, right? When you think about taste, you think about smell, you think about touching, you think about sight, and you think about hearing. So I'm touching on light and hearing, but you must be in touch with all of your senses in order to make sense of this world, right? It's some of you have probably been in experiments where you hold your nose, for example, and they'll give you a piece of candy, and you'll chew on it, and you'll have no idea. You can talk about the consistency of it, but until you release your nose, you're not going to really identify what the flavor is. And a lot of times, like licorice is one of the things that people use as an example. Put it in, I have no idea what that is. Okay, release your nose, and then bam, the olfactory senses kick in. So, oh yeah, that's licorice, right? And the list goes on. So it's not only the senses, but it's the interaction, the confluence of these senses that makes us, helps us understand the world that we see and hear. So one of the things to point out, and this thing is loaded with opportunities for quiz questions and for final exam questions. So for example, starting out with rods and cones, our night vision and our color vision in terms of where we come in with where the rods and cones are most sensitive, right? Cones, I just think cones color, right? Rods are for light and dark, right? So when you walk into a movie theater, right, it takes you a little bit of time for your eyes to accommodate for the light in there, and it's always fun to see people come in after the movie sort of started. You get a dark scene, and they're just standing there. They can't move because they can't see the seats, right? They're just like wait until something brightens up the screen and they can see the seats. But for you, that takes about 5 minutes or so. But as you get older, it takes a bit longer. On average, around 15 minutes, really to accommodate to low light conditions. And this is where the rods kick in, and you can see where the wavelength is coming down at their peaks. And we'll get into the color spectrum in a bit. But the idea is that can we use this information to help us with regard to ergonomics and safety? Is there anything in this room that jumps out at you that's colored a certain way that indicates safety? And is there a reason why it is that color? Yes. The exit signs. Why is the exit sign not red? It should be red because you would think, wow, red, it's like, emergency, right? It's an exit, get out of here, right? There's one at the back. But it's kind of a lime green, isn't it? And do we know why? Yes. I'm sorry. Go ahead. Yeah. It's easier in the dark? No. Not true. No, not true. It's easier to see. Stop right there. But there's a reason that it's easier to see, and that's good because then I can tell you why. Yes. Okay, there's a systems approach. You're getting ahead of the curve now. You're getting really sophisticated about a systems reason behind it. But actually, I'm just really talking about the physical aspect of why it's this color, and it's illuminated. Yes. Because green represents go. That's not a bad idea either. No. You've already had one in the back. The lime green, and why can you see it better? Yeah, that's exactly right. Well, it's not only the wavelength, but see where I've drawn the arrows straight down? Right here, if you follow me, see the color vision right there? And of course I'll change it out for you here in color. Hopefully it's going to do that. Yeah, all right. So see, is basically we're looking at normalized values right here. The higher the peak, the greater the concentration, and the more stimulated either the rods or the cones are going to be based on that peak, right? It's very curve related. So as we start getting away from that, the cones and the rods are not going to be as stimulated from that peak value. So this shows us a peak value for night vision, and it shows us our peak value for color. And so the idea is that if we really want to see things, and we're going to distinguish this night and day. Okay, so we're talking about day right now, is that we come straight down. This is for darkness and light, okay, in terms of night vision right here. And this, our color vision, this is for color, what we see the X sign. The idea is that we want things that are easiest for the eye to see, catch, when we see that the peak value is at the top. And it turns out that when you go through this, that the best daytime color for seeing is exactly what you see right here. It's light in here. Of course, it's backlit, obviously, because if something were to happen now and you want to get out of here, obviously that has to be lit up. If this is not backlit, it doesn't help you, right? So that's the reason it's lit like that. So if we, and I'll show you the reason behind that. This is the best color for night, right? Why? Light and dark. Yes? It's lime green. I'll show you that in just a second. So keep your powder dry back there, because I'm going to show you exactly why that is in a second. Okay, but first I want you to know, and the quiz question is, lime green for daytime, right here. For nighttime, it's white. What color are fire trucks? Well, it varies, right? Some are lime green, and some are red. Most of them around here are red, right? In the daytime, red elicits excitement. Anytime, especially among males, when males see red, they get excited. Women get excited too, but it's a different kind of thing. So, but anyone sees red, right? It elicits excitement. It says danger, whatever, flashing and so on. And people are conditioned to say, okay, that's going through. It has nothing to do with the physiology of the eye in terms of the rods and cones. It's about a conditioned response that we have. The problem with red at night is that you don't see it as red unless you bring it to an area that's lit up. So that's why white, because it contrasts with the darkness, is the best color for night. Okay? So so it says basically, if you've got a fire truck running around at night and it's parked somewhere, you're liable to run right into the darn thing because it does not show itself as red. You don't see it as red. All right. So best for day, best for night, and then if we apply this, then color red. And I just mentioned this. It's the least visible of the colors at night especially. So optometrists note that for its high visibility, lime yellow, okay, should be used for fire and rescue vehicles, especially during the day. Now the upside of that is that because it's now moving into that spectrum, is white, as you know, is a mixture of all colors, right? So we're getting a little closer to that spectrum with this color. So at night, it's okay to have this. Obviously, you want to have white. It would be great if we had, emergency vehicles and fire trucks and so on to be able to change colors. And I believe that's going to happen in our lifetime. That we're going to be able to come out with paint that will be chameleon-like, and it will change colors, based upon the nanotechnology of the paint. But for the time being, we're having this recommended as lime green, in terms of what these rescue vehicles will look like. And you do see some of them painted that way. At night, white is the most visible. Lime yellow stands out, obviously better in cloudy skies, snowy backdrops, and so on. But the color red is perceived as black at night. Also, people have particularly poor peripheral vision for red shades. So getting out of peripheral vision, going over this direction right here, your peripheral vision is better for seeing this color. Why? Because you're at the peak form in terms of the response of the eye to that color. Yes? They look at the photoreceptors of the eye and how the eye is responding to it in terms of an electrical response. No, it's basically the rods and cones. If you go into the eye, you have the optic nerve, and you shine a light into it, and then you go the different color spectrum, and you see how the eye responds to in terms of that relationship. The other is that most of the cones, as it responds to this particular color, and I'll show you that in a second. See if I can get to it here. Right here, you see the visible spectrum. Look at where the visible light spectrum is in the middle. So as you see in the peripheral vision, you see Roy G. Biv. Remember that? Red on the end and then indigo and violet on the other side. So there's your longer wavelengths, your shorter wavelengths right there. But look at what's in the middle. See this color right here? So you're starting to get that blend. That's your peak response for the eye in terms of what it's easiest to see. So there's a physiologic mechanism, and there's our response to it in terms of how the eye is designed to see things in terms of color during the daytime. Okay? So this is not like new science. It's been out there for a long time. But it's just the way we were put together, all right, in terms of most vision. So let me go back. So the visual process then, the eyes adapt more rapidly when moving between dark and light spaces, but not from light to dark, as I mentioned, like in movie theaters. When you age up, 40 and over, we start to have loss of elasticity in the lens and flexibility, and what's called presbyopia occurs. And presbyopia is that ability to not see things or adapt to them as you are. So all of you sitting in the back, either I see a couple with glasses. Any of you back there with contact lenses? Raise your hand. Okay. You see okay from back? You see okay back there? No problem? Okay. I can, to be fair, for me, used to be able to pull this off. Didn't notice it when I was working on my doctoral degree at Michigan, the University of Michigan. I didn't realize that my eyesight was starting to deteriorate. And so what I did is a little trick. And I take your two fingers like this and then close the gap between the two and look at the letters up on the screen. And if they're looking a little blurry to you, they'll come into focus, because what you're doing is that you're shaping the light coming to your eye, and it's now becoming more clear. So it's actually almost like a lens corrective technique, which is really kind of fun to do. But this kind of tells you at your age, if your eyes are kind of pooping out a little bit right there, and all of a sudden you start to see the letters and they're more sharp, and this way it might be that you are on your road to vision correction, like me, for sitting in the back. So whenever I go to a meeting where I really want to pay attention and I need to look at the notes and so on, I'm going to sit up here. You know, it helps me to pay attention when I'm up here, but more importantly, I can see what's being shown. So that's where it comes in. So I'm a victim of the presbyopia that comes in, and now, heaven forbid, it's only been in the past couple of years that it's easier for me to read with glasses on as well. So now this whole idea of having to extend the newspaper out and read it, that kind of thing, because you have to get a little more distance there, because the eye is not adapting to the letters. So now I wear the glasses. Now I hate doing that kind of stuff, but now I can see both. So basically I'm into the bifocal area. So I can see distance and I can see close up. So presbyopia then is a vision condition in which the crystalline lens of your eye loses its flexibility, and it makes it difficult for you to focus on close objects. So electromagnetic waves. This we're looking at the relationship between velocity, frequency, and wavelength. This is the formula. I will not hold you responsible for memorizing that, but just know that when we're looking at the electromagnetic spectrum, and what we were talking about earlier is that how do we know that, for example, lime green, is something that the eye is most sensitive to? It really falls into this spectrum right here, where we're looking at relationship of the speed of light in terms of its velocity, what that frequency is, and we saw that frequency. And also its wavelength, if it's long or short. Red is long, right? Indigo and violet are shorter. So if that's true, and you haven't looked at a rainbow recently, what's going to be on the outside ring, and what's going to be an inside ring in terms of color? outside color is going to be what? Red, right? Indigo and violet on the inside, right? Unless it's a double rainbow, right? Then it's actually reversed. And that's just a reflection of actually coming out of that raindrop the second way, right? The second time. All right, so this is the spectrum I showed you a little bit earlier. And what's really fascinating to me is how small. Look at that tiny little spectrum that we can see things. So small compared to everything that's out there, from cosmic rays all the way up to power transmission, TV, and so on. And then the other ones that we can take advantage of, certainly in the science of what we do, are infrared and UV. Right? UV, of course, is the big thing now. Many of you are familiar with that in terms of its harmful effects on the skin. But we can also use it to our advantage in the sciences. And I think I might have something for you here on UV because I've updated this presentation just with 2 slides, just because I wanted to show you what we can do with this stuff. But it reminds us how little of the electromagnetic spectrum that we are in touch with on a day-to-day basis. But we can use instruments to give us a lot more information. So as you saw a little bit earlier, here's our radio, microwaves, infrared, UV, and then our short and high, and then a very small part of that spectrum, of course, very small spectrum right here is this going from red to indigo and violet. Here we go. Hopefully this works. You don't have this. I just put it in here, but I'll update it. But I just wanted to show you. I do a lot of different kinds of research and so on. And one of the areas that I've been pretty engaged with is with post-anesthetic care units and looking at exhalation of anesthetic gases, waste anesthetic gases. And the thing is with nitrous and other types of gases, anesthetic halogenated compounds and so on, you can't see them with the naked eye. But if you have a reference heat source, every gas has a heat signature. So in this case, if you have the right filter, you can actually see and visualize the gases. And if you have a Moran, which is also an infrared spectrophotometer that actually quantifies that exposure, it tells you what you're exposed to. And the key difference here is that you can talk to nurses until you're blue in the face and say, do not, I'll do this to Josh, do not get on top of the patient and do this because they're off-gassing and they're going to basically expose you as the day goes on. They say, we're nurses, this is what we do. Say, well, let me show you this. And so here you see a nurse. Here you see a patient that just came out of surgery. Hopefully it'll just work. Oh, man. Okay, let's see. On here, on this thing? Thank you, Mike. So here we go. You can see she's talking. She has just come out of surgery, and what you see coming out of her is nitrous oxide. This is not CO2 because it's very close to that spectrum because we have filtered out for that. But here we have this patient off-gassing the nitrous oxide. You can see the proximity of that nurse caring for that patient because that's what they do. She's just wetting the lips right now, coming out. And there she is. And then as you can see, this plume that comes out is that as they go on, they accumulate this exposure, the nurses do. And at the end of the day, they can expire in their own breath. They have this residual nitrous in their system. And when you look at the literature, everything from spontaneous abortions to fetal abnormalities to cancer are higher in operating room nurses, and now we're starting to see this as a new issue in post-anesthetic care units because from the hygiene point of view, it seems counterintuitive. Say, well, where's your source? Because a lot of times you're thinking, well, it's usually a tank or something of that nature. Said, no, your source is the patient himself or herself in terms of being a reservoir, and there's enough of a burden there to actually create a toxic environment for those nurses. This is a new discovery, by the way. You're not going to find a lot of it in the literature. I've written a couple of the first articles on this particular topic. But the reason for showing you this is that here we've moved into the infrared spectrum, and we can take advantage of that because our eyes can't see it, but our instruments can with the proper filters. Okay, now I'm stuck, Mike. Oh, okay. I guess I'm okay. All right, good. So moving on from that, then we get into specular reflections. We get into spread reflections, diffuse reflections, and so on. So when you look up the lights in this room, right, we have fluorescent lights in this room, and the light is coming down. In many instances, what you'll see are what's called egg crate diffusers to help spread out the light. In this room, what they've used is basically highly reflective metal, right, aluminum sheets to cast down the light so that you can see your notes a little bit better. And so the problem is that if you're in a room where there is a lot of glare, then it becomes problematic in terms of health issues. So here, in terms of your specular reflection, we have these are highly polished surfaces. Highly polished surfaces, good, that are perfectly smooth. The angle between the incident ray and the normal to the surface will be equal to that angle that's reflected by that ray in the normal. In other words, what you see up there, that light is basically coming off that angle of sheet metal is basically bouncing off that and coming straight down over to you, if you were to look at that. So that's the incident light that's coming down, and that's the reason why it's basically more like a trapezoid shape than in just a box, right? Because it wants to kick that light down to you. Spread reflection. This is polished surfaces that are hammered or deeply etched and engraved and spreads out rays as it reflects. So these, you've seen some of these. One of the things that comes to my mind is the disco ball, right? That basically seeing the light getting kicked out all over, shining off of it. That's an example of that. And then diffused reflection. This medium has a rough surface. Is composed of small crystals of pigment and particles. Reflection is diffused. The incident ray is reflected at a number of different angles. And this would be from inside now that you would say, I don't know if you've seen some of the LEDs that are surrounded, and you light those up and they send the light in all directions. Luminous intensity. This is candle power, the amount of light output emitted in a source in a specific direction, measured as a light source, and it's known as a candela or a candle. Luminous flux is the time rate of flow in which light comes from a light source, and it's emitted in all directions. And the lumen is the unit of light output from that source. So notice that there are different ways of measuring. One is the candle, and the other is the lumen. Lumen is international. The candle is more like ours in terms of the English units. So illumination levels. This is the density and quantity of the flow of light falling on a surface then. This is your in lux and the international system. And foot candles, as I mentioned, this is your U.S. customary or British system for measuring things. So you're going to see a lot of things when you pick it up is that simply you can convert either from foot candles to lux. But since we're very used to dealing in inches and feet and so on, I'll expect you to go back and forth because the conversion measure is pretty easy, and I'll show you that in a second. And when we look at illumination in foot candles, it's either in meters or in feet, and D is the distance between the light source and the illuminated surface. So when we talk about foot candles, so we're talking about, okay, you have a light source, let's say a candle, let's just make it literary, so you have a candle, and you're 1 foot away, so that's 1 foot candle. And then you're 2 feet away, 2 foot candles, but they're going to be different in terms of the illumination. Why? And you got to write this down, because of the inverse square law. All right, so the further out you go, it's not linear, it's basically the inverse of the square law of that application. And I'll show you that in just a second. So 1 foot then equals 1 lumen per square foot. 1 lux equals 1 lumen per square meter. Okay, so big difference there. And so I may give you something like this in the exam and ask you to do this. So you definitely want to circle this slide and say, here's my light source, and I'm at 1 candle or 12.56 lumens. There's my light source, and it's the basic illustration of the inverse square law of light distribution. So when you go out 1 foot, right there, you look at, say, you got 1 foot candle out, right there, and your illumination, or you get 10.76 lux from that, and you go out 2 feet on this. Notice that you've gone down. You've got 1 foot candle, 2 feet out. Now you're down to 1/4, and then if you go out 3 feet, you're down to 1/9. Right. So basically, as you get equal distances out from the light source, that light illumination from that source drops considerably, not by the distance, but by the inverse square of that distance. So just take a look at what these are. At 1 foot. 2 feet. 3 feet. And these values right here. And that information then, 1 foot candle at 1 feet, 1/4 at 2 feet, 1/9 at 3 feet, tells you about the illumination as a function of the distance away from that source of light. So we get into brightness. Luminescence then is the amount of light per unit area reflected or emitted from a surface. Your international units then, this is your surface area is in square meters, as I mentioned earlier. And we're looking at the British units then and measured in foot lamberts or in foot candles, as I talked about a little bit earlier. And we're looking at reflectance versus illumination as a function of luminescence. So illumination and reflectance then will give you luminescence. So the idea is that in order to get the light in this room, if you think about it from a human factors point of view, that notice you got the light coming straight down, but look at the color of your desk, right, which are brown. Now, a lot of them, if you have, so you see some of the more modern rooms are going to be a little bit lighter color, but the idea is not make this a reflective surface so that you might have glare coming back up and hurting your eyes, right? So it has to be basically a flat or a matte kind of finish so that what you're looking at is just your notes and not having this come back into your eyes and causing problems. So reflectance then is a measure of how much light is reflected on a surface, and it's a ratio then of brightness or luminescence of a surface to the illumination level on the surface as it's measured at a percentage. So reflectance here then, we're looking at pi times luminescence times 100, and reflectance, if we're looking at in British units, at pi times the luminescence over the illumination times 100. So circle this one right here. And if I gave you a question and I asked you, calculate the percentage of reflectance off this particular surface, 2 ways to do it. One is that just have a light meter, right? But if I gave you the information in terms of what's my percent reflectance, well, first of all, I have to give you the luminescence, right? You know pi. And then you divide that by the illumination in foot candles and multiply that times 100, and that gives you the percent that's being reflected back. 6 factors come into play for lighting. I will hold you responsible for this. Contrast, size, time, luminescence, color, and visual acuity. Each of these is a factor, and all of you have experienced this. So one of the things that is a take-home note is that when you're doing your project presentations, tiny print or showing me a slide with a very busy background is not the way to go. So as you can see with my slides right here, I don't include graphics as a standard background. It's busy, it's annoying, it's distracting. What I try to do is give you something that's pleasing to the eye. Blue color is pleasing to the eye, but the letters that I show you, either in white or in yellow, contrast with that background, and they're large enough, the font is large enough so that you can see it in the back. Part of this has been thought out in terms of making sure that it's not so small that you can't see it. So your take home here is that pay attention to contrast, pay attention to size for font, pay attention to time if something is moving, right, through it. How long do you have to look at it? Then, of course, brightness counts. That's one of the reasons why when I give you presentations, right, I don't go with this. Why? Because what happens is that you lose some visual acuity, right, on the bottom as a result of the foreground being now just a little too bright, a little too harsh on the eye. If I go this route, then it's a little too dark because you can't see your notes as easily, right? So it's not perfect. I would love to have a dimmer switch up here, but that's about right, right? What's in here?
Uh-huh. Yeah,
But
it only works when you're in the dim setting.
Let's see what happens. Go ahead, bring it all the way up.
Well, that works real well. But
Not the best, right? So I don't know. Some of you are probably like more soothing to be a little darker, but yeah, I forgot about this because it's not the best, right? In terms of making. But probably if you really wanted to see more detail on the slide, that's probably not a bad option to have. At least it doesn't. You don't go that way, right? Which is not good. All right. Thank you, Mike. All right. So contrast then is a measure of your luminescence difference between a target, the task. Okay, so this would be what you're looking at right now, your notes, or up here on the board. And its background is defined by the following equation, and I'm going to hold you responsible for this. Your contrast percent is basically what your background lighting is minus the task or the target, right, the lighting of the target, divided by the lighting of the background times 100. Very simple. Just remember your background minus the target divided by the background times 100, and that's going to give you your contrast that you need between what you're looking at. So in this case, it would be the blue background right here versus the letters that you see. Or it would be the lighting here, what we're looking at as your contrast between your sheets of paper and the ink that you're using to write your notes. Then visual acuity refers to the sharpness of vision. And I guess I have to be consistent, right? See how the yellow stands out, and you've corrected me on this a couple times, and I appreciate that, is that red is okay, you can see that, but yellow, obviously, because it's a higher contrast, right, and it's sharper, you can see that a little bit easier. So, I try to switch over to that where I can. When I'm writing on white, I'll use red to highlight it a little bit better. Why? Because the yellow sort of fades with the white. So, the ability to discriminate black and white detail. Example is the Schnellen letter chart, and all of you have seen this. It's placed about 20 feet from the subject. I will hold you responsible for this because now we're looking at what people can see further than a distance of 20 feet and what they can see less than 20 feet in terms of vision correction for distance sight. So in this case, we're looking at a person who has a score of 20 over 15 is better than normal, since a detail that is normally seen at a distance of 15 feet can be seen by the subject at 20 feet. Lock that into your heads. The number of feet is in the denominator is the key. If the person tests 20/25, what does that mean? Something that's at 25 feet, right? They can't see. They actually have to get 5 feet closer, right, to be able to see something that most people would see at 20/20, right? Basically 20/20 means I can see from 20 feet, I can see without any visual correction a letter size that would indicate they could be seen from that distance. So denominator is the key. So if I give you a quiz question or an exam question, and I say if I give you something 20 over 30, or if I give you something 30 over 20, what does that mean in terms of that person, vision? Are they farsighted? Are they farsighted in a superior way, or are they not farsighted? Do they have issues in terms of that vision distance? So this tells you right here, that slide is an important one. This is your Snellen chart right here, and as you get right down, these are distances at 200 feet. 200 all the way down, 20 feet. You should be able to read that, at a distance of 20 feet back. Some of you probably won't be able to see that in the back of the room, but some of you have really good vision. You're younger. You can probably be able to read that bottom chart, so it means you're even further back, or even better than the ones that can see, at 20. So this helps basically set the stage for what you can see at what distance. So visual acuity then, it's a means of focus, your vertical angle at 1 degree. The middle field, the vertical angle is 40 degrees, and the outer field, the vertical angle is 40 to 70 degrees. So what we're looking at in this issue right here is movement detected but not color. So we're looking at vertical field, looking at what I'm talking about here, 1% just straight on, 1% off. The next one, in terms of middle field, we're looking now 40% out, like this, okay? And then outer field, 40 to 70%, we're coming out about here, right? So what does this mean? It means that if someone is moving over here, right, and you're looking straight ahead, you will not be able to see that in color. You'll see movement, but that movement will be more in the rod area, the light and dark image, rather than say, I saw someone moving over here. Can you tell me what color they were wearing? If they were over here, chances are their story is not very credible if they said, I know they were wearing red. Unless you looked at them, you don't know. You say, I don't know, but I did see movement. Okay? So this is an important fact in terms of visual acuity, visual field, and what you can see. Yeah. That's correct. Yeah, the visual angle, yeah, of actually from here to here. Yeah, that angle right there, that piece of the pie. Yeah, it's not like the biomechanical part that we talked about earlier in terms of being in the mid-sagittal plane. So accommodation then provides the ability to focus on near and far objects. As I mentioned, mine are not as accommodating as they used to be. Yours are probably pretty good. Adaptation, the ability of the eye to change in light condition takes about, as I mentioned, 15 to 30 minutes for become what's called dark color adapted. Light adaptation is much faster. It takes about a minute. So, for example, when you walk into a movie theater and you're all black, I can see within a couple of minutes an object here, right? Like you can see the chairs, I can see that someone's in that chair. But if you were to ask me, say, what color are you wearing? I would have no clue until I just had a little more time to color adapt and say, oh, I can see you're wearing black and red, right? And that's really based upon the background light. It's not a totally dark theater because you're seeing actually something, the lighting from the stage, but you have to wait a little while for those cones to kick in. Okay, so the rods kick in right away, the cones take longer. So glare, we have direct, indirect, discomfort, disability, and photostress. Results from high luminescence, insufficiently shielded light source, that's your direct glare. This would be, like the sun, right, coming in through the windshield, which, by the way, did I bring this up earlier? When you're growing up and you buy a home, what factor are you going to consider? If no other ergonomic thing that you remember, what are you going to remember? Buy the home on what side of town? The east side of town or the west side of town? Why? Because you always want the sun at your back, right? If you can. Driving to work, and when you're going home, the sun's going down, you want the sun at your back, you're heading home, right? So now it's in the west and you're heading home, you don't have those glare issues. There's so many people that settle on the west side of something and they're just like always, calling it, not good. They got to think about it. If you can. Direct glare, Refracted glare that results from images of high luminescent sources reflected by specular sources in the visual field. This is basically something like a mirror and reflecting. It was really interesting. There's a group, I think and it is in Norway now that I recall this, that from I think it's around the beginning of October until about the April, they are without sunshine. I mean, it lights up, but the sun settles behind a mountain because it's so low, right? I mean, you can think about Norway. It's so low, and they're in a valley, and they got a river, and they have a water source, and it's nice, but they get so depressed in terms of their moods because they don't have any sunshine, right? And just all upset. I'm thinking to myself, well, why did you build a place there? Crazy people. And, well, they're Norwegian, and so on. But what an enterprising guy did was he, up on the mountaintop where the sun does shine, they built a huge array of mirrors. And they focused the mirrors down in the town's square. And so for pretty much the whole year, they've got this little spot of sunlight. It's about, 20, 30 feet, in diameter. And people are all standing in there going like this, only better than that. And it's just amazing. Just like, oh, well. I'll get into the mood thing a little bit later. But anyways, that's your indirect. Discomfort glare, obviously feeling annoyance and eye strain. This is where you're not really sure of where this is coming from, but it's just reflecting off something and causing issues. Disability glare, diminished visual performance and ability to see. Again, the same kind of thing now, sun coming into the windshield in some way, and it's now reflecting over other sources. And then photostress glare, intense light source that causes a delay in recovery of the visual system after a macular region has been constantly stimulated for a light source. Takes about 30 seconds to recover. A lot of times what happens is that special forces will use these light bombs. When they throw in, they don't want to take anybody or kill anybody. They just want to disable them, and they'll just basically throw in a light grenade, and it goes off, and it basically freezes them because now they're photo blind. So that's an idea of photostress. General rule: avoid glare. The angle between the horizontal line of sight and the eye line of sight should be greater than 30 degrees. Ooh, I'm going to hold you responsible for that one. In other words, when you think about the question you were asking me, right, about this field right here, 40 to 70 degrees, think about that. You're now taking it just outside that 30 degrees. Why? Because you don't want that light coming in within that source. So if you've got your desk facing out this way, the light's coming right in there, you have to move it at least 30 degrees. But most recommendations are, because we're orthogonal in our building, is to move it 90 degrees, right, over here so you don't have a direct source. And don't go 180 degrees because now you got the light banging off the screen, right? So the idea is to move it there, but the idea is that the minimum in terms of this kind of glare, at least 30 degrees or more. Lighting surveys, we've done description of workplaces, general lighting. I actually had a group a couple years ago that went over to some of the nursing homes and I don't know, isn't it University Village or something like that? And everyone like down on campus, right? Yeah. Okay, and they have people with various levels of needs and so on, from fully able to needing daily care. And they did a light survey over there, ground lighting, especially at night. And it was great because they found it to be, insufficient. And they did the light meter thing the whole bit. And as a result of that, they upgraded all of their ground lighting over there to protect people not only coming to see them, but ingress and egress, on and off that property. Pretty cool study as it turned out. So you want to describe the workplace, general lighting system, what you used in terms of the instruments for measuring that. You want to be quantitative, in your measurements, and subjective in the evaluation of the lighting in terms of how people feel their comfort is, because it's a whole different animal to dealing with a population my age versus a population your age. Minimum illumination, I'm going to hold you responsible not for all this information, but just a little bit in terms of general construction lighting. Look how low that is, 5-foot candles. Then we start climbing up. Indoors warehouses, only 5. First aid stations, 30. Fine assembly task, 100. That's really where you want to be for you when you're studying at night, and you want to have good lighting during the day. you really want to be up or around there, at least 50 or higher in terms of foot candles. But in terms of looking at your notes and things like that, here you are reading materials, etc., around 50. And then it goes back down stairways, sidewalks, corridors, and back down to 10. And here's an example of contrast. Where's contrast? This gives you an idea of you're trying to read this thing. If you have a busy background, all these fancy fonts and so on, look how it takes away from the clarity in which you're trying to communicate versus over here. Good contrast, no busyness, and so on, so with the background. Keep that in mind. These are lighting from general to local, so this would be like in your house. This is going to be like in a restaurant or so on. So here you see what I call the egg crate diffusers. Here's a recessed light panel, or it can be extended. Track lighting right here. Use your fluorescent lighting. Here's your egg crate. Another example of that. Wall mounts. Here's a little more diffuse. Desk mounted, and basically a standing lamps and so on. The game changer is really kind of interesting. That the game changer that's occurring, and I don't know if you know about this or not, is the LED revolution and its use in farming. So I was at the President Daniels' house last week, Thursday, and I was listening to a talk from Gabiza Ijeta. He's the one that won the World Food Prize a couple years ago. A class act, by the way, really neat guy. And it's always fun. So I had Vic Lechtenberg, who is the acting provost, and Tim Sands is now, but he was the acting provost about a year ago. The president was talking with me, and Gabiza Ijeta was talking. And we were talking about lighting and the LED revolution now. It's places like in China and in India where they're having vertical farming, and basically because there's only 10% of the land is worth anything in China. The Chinese have gotten very clever about what they're doing, and they've switched over to LED lights, but they now have these vertical farms like high rises. And they go straight up, and they have all these LEDs right next to them, and they had the hydroponics working. And if you want to see how this works, you go down to Disney World down there, and they'll show you all that stuff, because the idea has been out for a while. The LED technology has only really come on in recent years, but it doesn't get hot, right? The LEDs don't get hot, and they last a long time, and the energy consumption's low. So here you have these entire cities lit up, right, cranking out vegetables like there's no tomorrow. It's amazing to see all this stuff happening, and this has only occurred in the last 3-4 years. Can you imagine 40 stories high, and it's composed of nothing but vegetables, right? And lit up around the clock lighting, because as you know, if you go to Beijing, you don't see the sun very much there, all the pollution. But they have these LEDs that are making a difference. Just amazing, fascinating. Anyway, little aside. I don't know. I get excited when I hear that kind of stuff. Neat. Visual difficulty, size of details, perform a task. There are computations that you can do that for how far away the letter size has to be. Importance and frequency of each task, time available, worker comfort, obviously age is a factor. Economics and feasibility, as I mentioned, the LEDs. Amazing, that technology. General rule, minimum level of illumination for the workplace where multiple tasks are performed must be determined based on the most difficult and critical task. In other words, when in doubt, light it up more, right? And I think this is the quality. This just, Sandra sent me this. Mike, I might need your help on this again. Let me see. Does that do it? No. Hang on. Let me see if I learned anything from you. Is it doing anything? We don't know. Yes, it's doing something. I think it's the last slide. We're going to do the quiz. As you know, with Molecular Hub, we had over 1.2 million hits on this thing just last month alone. So it's an amazing site. Thank you for joining up as members. And occasionally look at it, because I definitely think it's the future. But one of the things that I want to tie in today is this hospital room lighting may worsen patients' mood and pain. And what was interesting about this is today, just came out, and it talks about an average whom are exposed to so little light during the day, their bodies cannot adapt to a normal sleep-wake cycle. So here's a situation that's come up about the idea of how much illumination that you have in the rooms and so on, and the idea is that when you're sleeping it should be totally dark. When you're awake it should be very light, and you shouldn't have flickering on and off, shouldn't have the door open to the hallway and so on and so forth. There's noise issues that come into play there. But here's a situation really where they were dealing with light and dark and moods and patient satisfaction in hospitals. I thought that was pretty cool. Now some of you have probably seen mood disorders as a result of the decreasing amount of daylight that we get as we go into called seasonal change disorder. But there are some companies out there that say if you have the more full spectrum of lighting that you're going to feel better. So you have all this artificial lighting coming in that basically tries to mimic the sun and make you feel better. There is some research on that. The jury's still out, as if that's really enough light coming in. In other words, the spectrum is there, but is it really enough to affect your moods in a positive way? So there have been some studies along that. But this is one of the first to come out and really look specifically at hospital rooms and light and dark and so on. So anyways, I wanted to share that with you. Kind of fun.